And we're off to the races again. Now we're talking about discrete probability distributions, and we're continuing with properties of binomial distributions. So here we go. Just a reminder here, this is a typical binomial distribution with n is equal to 5 and p is equal to 0.35. Now remember, before, if we had n is equal to, p is equal to 0.5, then we would have had something that would have been a much more symmetrical kind of distribution. Whatever was on the low side would have been more like what was on the high side, and that's not very well drawn, but you can see what happens whenever we get the p different than 0.5. we start seeing a little bit of a skew. Let's see, the expected value, that simply means the mean, is, here we go, our expected value. We can calculate that quite easily as however many n's we've got times that probability of a success. So it's just n times p. The variance is going to be just n times p times q. And your book actually works through the derivation of these quite nicely. Now, we can also figure out the probability that event A occurs at most some j is less than the total number of n times is given by f. This is a cumulative distribution function. So really what we're saying is this event, here's the probability that an event that we have 0, 1, 2. So let's say it's 2 or less, right? You know you would add this probability amount, right? Plus this one, plus this one. So in other words, we're doing a summation. So we just sum from 0, from x is equal to 0, to whatever our j is of the probability, and we calculate the probability for each one of these as the combinatorial of n choose x times p to the x times q to the n minus x. This is just a little reminder here, the Bernoulli trial, also known as the binomial experiment. Remember, it's n to p what I. So we've got n trials, 2 possible outcomes. Each one has a p, a probability of success that's fixed. And lastly, the trials are independent. So one doesn't affect the other. That's just a quick reminder. So let's look at problem 375 in your book. First thing, well, it asks, for each scenario, state whether the binomial distribution is reasonable for each random variable. So we really are asking, does Bernoulli live or die, right? Is Bernoulli present in this situation or not? So first off, we have a production process produces thousands of temperature transducers. Let x denote the number of non-conforming transducers in a sample size of 30 selected at random from the process. So let's look at this. We've got thousands of transducers. We're picking 30 of them. It's at random from a huge sample. So have we got a set n? Absolutely, it's 30. So is it 2 outcomes? Well, let's see. It either conforms or it doesn't conform. Yep, so it's 2 outcomes. Do we have a specific probability? Let's see. For this particular sample being conforming or non-conforming? Well, the fact of the matter is, whatever that probability is that we'll have a non-conforming transducer, it's us selecting a transducer out of there is not going to change the probabilities, right? It's not as if we knew we had a certain number of transducers in there, and so taking it out will change our odds. And likewise, once we pick one transducer out, it's really going to be pretty much independent from whatever the other, like let's say we pick transducer number 1, then we go and pick transducer number 2. Because we're picking from thousands of different ones, it's very unlikely that they will both be affected by the same glitch in a process. However, if you only pick from a batch of 50 and you pick 30, it's actually quite likely that you could pick transducers that were produced close together. And so if there was a glitch in the process, one might have a problem, and then the one you selected next to it might also have a problem. In other words, they're not independent. So you would have to know a lot about the characteristics of the problem in order to make these kinds of judgments in reality. But this does give you a sense of how to start looking at some of these kinds of problems, and that you can apply these ideas to see whether the approach you want to use, using binomial distributions, might be appropriate or not. Soon we'll see some distributions where binomial wouldn't be appropriate. So let's go on. The random variable x has a binomial distribution with n is equal to 10 and the probability is equal to 0.5. So determine the following probabilities. This problem is just a standard classic problem for you to give you a sense of how do you do an ordinary problem. Okay, so we'll start with probability that x is equal to 5. We're doing this with n is equal to 10. So we'll just say that the probability, this is a probability that x is equal to 5 is just, well, look at this. It's easy. 10, that's the n. Choose 5, that's our x right there. And we'll take p raised to the x value. So p is 0.5. X is 5. And now we'll take q is 0.52, and it's n minus x, so we've got 5 right there, and there we go, 0.2461. So that's A. Now, the probability that x is less than or equal to 2. So, now look, this is where it gets sneaky. You want to say that this is actually the same as the probability that, well, we could first have x is equal to 0, and then plus the probability that x is equal to 1, plus the probability that x is equal to 2. Right? I mean, this seems really common sense when you see it laid out here, but you'd be surprised at how many people forget this x is equal to 0. Sometimes they'll even forget x is equal to 0 and x is equal to 1, and they'll just do the 2. But it's really important to remember that if you have that less than or equal sign, it does symbolize something. So anyway, we'll write that down as probability of x is less than or equal to 2 is, well, look at that. 10 choose 0 times 0.5 to the zeros times 0.5 to the 10. And then we'll add 10 choose 1, 0.5 to the 1, and 0.5 to the 9. And now we'll have 10 choose 2, 0.5 to the 2, and let's see, can I squeeze that in there? Not quite, so I'll put a little, 0.5 to the 8. So there we go. Now let's try C. Okay, now this is the other trick that we can pull on you, so you want to make sure you recognize that. The easiest way to do this is just to say, well, we know that 10 is the maximum. So if it's 9 or greater, then essentially that's the same as probability. Well, we'll put this probability x is greater than or equal to 9 is equal to 10 choose 9 and 0.5 to the 9 and 0.5 to 1 plus 10 choose 10 to the 0.5 and 10 raise to the 10th power and 0.5 to the 0 power. And I should be putting all the results here. Sorry. This is 0.017. And this one was 0.0547. And the first one, we got that one. So one thing I want you to notice out of this is, look, 10 choose 10. If you have 10 choose 10, you know, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have to choose all 10 of them at once. How many ways is there to do it? One way. And we can see, look at this. That's actually 10 factorial over, if we look at r, what is r? R is 10, so it's 10 factorial over, well, this one is going to be 10 minus 10 factorial. Well, that's 0 factorial. By definition, 0 factorial is always equal to 1. So it's 10 factorial divided by 10 factorial, so there's only one way to do it. So whenever you see 5 choose 5, 8 choose 8, 195 choose 195, whatever that is, you always know it's 1 right there. And that's a handy thing to know. So now let's do D, last one. It is, let's see, probability of 3 is less than x is less than 5. Well, I didn't do that very well, but we'll say it is just, well, look, we've got that less than or equal to right here. So that says we're going to include this one, we're not going to include this one. So we've got 10, choose 3, times 0.5 to the third, and times 0.5 to the 7, plus 10, choose 4, 0.5 to the fourth, 0.5 to the sixth, and so that turns out to be, well, we'll just calculate it out. It's 120 times 0.5 to the 10 plus 210, 0.5 to the 10, and that's 0.3223. So voila, we have it. And hopefully that problem, that was just a good bare bones walking through all the different ways that you could do a standard set of questions involving the binomial distribution. So now let's move ahead. Okay, now here's another of that series of problems from 375. This one is E. It says, let X denote the number of correct answers by a student taking a multiple choice exam in which a student can eliminate some of the choices as being incorrect and some answers, and sometimes they can actually eliminate all the incorrect choices. So we've got A, B, C, D are the possibilities, and sometimes we might be able to eliminate C and B. Sometimes we might be able to eliminate only, sometimes we might be able to eliminate virtually everything, or other times we can't eliminate anything. So we can tell in that particular case we don't have the same probability. That's a problem. So it means that the standard binomial distribution in this case does not apply. So now let's go on to another kind of one of my favorite problems. 12 people are given 2 identical speakers to listen to for differences, if any. Suppose that these people answered by guessing only, which means it's 50-50 odds that they'll claim to have heard a difference. Find the probability that 3 people claim to have heard a difference between the 2 speakers. What I like about this problem is if you're like most people, you'll go, how on earth do I set this up as a binomial sort of distribution? I don't even see where to begin. So I think if I walk you through this problem, it will really help you to see where you're supposed to go with a problem like this and how the binomial distribution does apply. Okay, now first off here, we've got 12 different people, and so what that does is that tells us that n is equal to 12. And what these people are doing is they're guessing that they've heard a difference. So the probability of them saying, yes, I heard a difference, is 50-50. So that's our probability. Now, wow, we're told that what's the probability that 3 people claim to have heard a difference? What's the probability that x is equal to 3? Oh, okay, we've got it. We can say that probability that x is equal to 3, and this is a binomial. If you look at it, the odds aren't changing. We know what our n is. We know what the p is. Each is thought to be independent from one another. So this is a binomial distribution. And we can write 12, choose 3, times, well, 0.5, that's p, raised to the 3rd, and then it'll be 0.5, this is q, times 12 minus 3. And if we figure that all out, that just turns out to be 0.537. So there you go. Not too bad. Now let's go on, and we're going to see, we're going to try problem number 3.84 out of your book. And this one says that we've got an electronic product, contains 40 integrated circuits. The probability that any integrated circuit is defective is 0.01. We've got independent circuits. The product operates only if there is no defective integrated circuit. What is the probability that the product operates? N2pi. Let's look at that. Do we have n? Yep, we got 40. N is equal to 40. Do we have only 2 outcomes? Well, it's either defective or it's not defective. So we're good there. Check. What about the probability? Yep, the probability any integrated circuit is defective is 0.01. So we've got P is equal to 0.01. Check. Independent? Well, it says they're independent. So yeah, that's a check too. So we can use the binomial distribution. And if we do that, we can just lay it out with what we're really looking for is that we want no defective integrated circuits. So we're essentially wanting that x is going to be 0. Okay? Probability that x is equal to 0 is going to be, well, 40, choose 0. Turns out that 40 choose 0. We're not going to choose any of them. So let's parse that a little more carefully. 40 factorial over what's r? Choose 0 factorial. And then this one is going to be what? N minus x, which is 40 factorial, Oh, wait a minute. Well, we already worked this one. We know it's 1. So this whole thing turns out to be 1. Okay, well, that was just interesting. Okay, so now we're going to have 0.1 raised to the 0 power, and 0.99, well, and of course this turns out to be 1 too, and we've got 0.99 raised to the 40th power. Work that all out on our calculator, and it's 0.6690. So all of that, and it wasn't too bad at all to figure out.